Okay, so then I'd like to welcome you. You know me already. I'm through the week here. I've been here. My name is Arina Heinzig, and I said I'm from the German Aerospace Center. I was based there in the beginning, and then I switched to ETH to be a professor, and I'm doing mainly Earth observation. I'm in the department or in the Institute of Environmental Engineering in order to provide people of these environmental sciences a little bit tools, remote sensing tools, and how to use it also in their daily life or even in the profession. Okay, up to now you have heard quite a lot of different imaging modes and techniques. So you have heard about tomography, multi-baseline approaches, polarimetry, and Paul-INSAR yesterday. And yesterday we even had a little bit an application associated to Paul-INSAR, which is forest height. So forest height is one of the main applications we use it. And yesterday I was already saying also, so why are we doing all these interferometry, tomography, and polarimetry and interferometry, Paul-INSAR, is actually because we would like to understand volumes, right? Everything that we do here is because we are penetrating. So that's the main assumption and the main concept actually why to use tomography or even Paul-INSAR is to be able to penetrate somewhere and to get information content about the volume itself. So that's the main idea why we use this. Good morning, good morning, good morning. Okay, and now today we will have an application part. So I start a little bit with the cryosphere, and within the cryosphere I selected actually one parameter which we are working a little bit on it. It's snow height estimation. It's quite simple. And I'm not using P-band in the moment, and you will see why in a few moments. So this means you can also use different sensors. I mean, we focus a little bit on P-band for this course because biomass was just launched, and there's new data sets, fully parametric data available. So that's, yeah, in principle, very great to explore them a little bit. So you're very in the beginning. You're one of the first, let me say, students and courses which using really biomass data, right? Most of the people are still not aware of how to use these data sets. So therefore, we focus a little bit on this. But I like to show you that you can also use other data sets and probably also reduce amount of polarization capability, right? In the moment, you have heard about it's great to use fully parametric data, but what I'm using here is a reduced set. So that's in principle the main idea, to show you also other data sets and a reduced amount of data sets. So my lecture, or let me say my course here, is a little bit focused on why is SAR good for snow parameter estimation. I will introduce it's called copol phase difference, which I call CPD. So you will see it quite often in the slides. It is called CPD. I'm using Tiny-Mix data in this, which is a copol system. And I'm focusing on the Aletsch Glacier. You see here already an image of the Aletsch Glacier. What you see here is in principle the glacier itself. So the glacier has 3 arms here mainly, or even 4 arms. So 1, 2, this is the main lobe, and then here we have another lobe. And this is the upper part here. And if you go then down, so that's the tongue of the glacier. In principle, this is a lower part of the glacier. And everything beside, you see already this typical radar effects, right? This is mountains. It's surrounded by mountains. And because we are looking sidewards, right, we have these very, very typical geometrical effects where we are calling it either foreshortening or overlay, so layover in principle. These are the mountains where you see first sometimes the peak and then later the bottom of the mountain. Like this, it looks like you have a swap in of a mountain to display to the other part. So that's a little bit typical for radar images. Okay, and then I will go also provide you a little bit a view that how we model snow also. So we're always trying somehow to understand the physics behind. So it's not only using data and analyzing data, but we try then to model the observable that we get from the data in order to understand the physics. So therefore, I'm also showing you, in principle, a model later on. Okay, let us start a little bit why radar for snow. There are several reasons. So if you go to the optical domain, you know already, right, optics is also providing kind of very good information content, but it's a different kind of information that you get. And I would say even sometimes it's very complementary. So I would not say radar is better than optics, this not, but it's very, very complementary. You get really different information content. But the main difference is, as I was just trying to figure out before, is that you see only the surface, right? You can't really penetrate into the snow very well. And this is why, in principle, it's a little bit limited in terms of what we like to do. We would like to see snow depths. And if you like to see snow depths, you need to penetrate into a volume in order to get information content of the volume. So therefore, the microwaves, it's great because it's penetrating into a snow. But this is only possible when, somebody knows? When do I able to penetrate into snow? Somebody knows? If the snow is dry, yes, that's a point. So if I have wet snow, so it means it is very warm, then you have in principle a very wet area on the surface, which means the dielectric constant is very high, and then you can't penetrate, right? That's point. Therefore, microwave only works when the snow is decent dry so that you can really penetrate. And the other point is not only penetration, it's depending on the wavelength that you use. And in this case, if you like really to be sensitive to snow, you're going to higher frequencies, and higher frequencies here means really you're going to 5 to 50 gigahertz. So which means it's in the range of, C-band is 5 gigahertz around, X-band is around 10 gigahertz, right? And even you go higher up, KU, KA band, so this is in principle the range that you do. However, also in these if you go to very, very high ranges, right, then you would still have also some problems with attenuation due to the atmosphere, right? You get atmospheric contribution, so you need to be a little bit carefully here. If you increase in principle your range of frequency frequency in this case, then you get more and more attenuation, and therefore only until 50, because then you have already so much atmospheric disturbance inside that you can't really propagate through this atmosphere. Okay, what is also typically is in principle, what is the main interaction between the snow and the electromagnetic wave, right? This could be also very important to you to know, and this is in principle this figure that you see here. So that's a main figure where you in principle have a snow layer. This is what you see here. You have a ground, you have a snow layer, and then you have this air interface. So the scattering is going actually, if you look for intensity, so radar backscattering intensity, then you have an interaction between the first surface air, right? And then you have interaction within the snow, which we call volume scattering. You know this already. Or you can have ground to volume scattering, or you can have only ground scattering, right? It's a little bit depending what you get, but this is in principle how you would get in terms of scattering mechanism, what kind of scattering mechanism you get in an interaction between the electromagnetic wave and the snow property. And this is very dependent, so this interaction is very dependent on the temperature, as we just said before, right? If it's very warm, then we have a problem because we can't penetrate, but the total penetration is very good, right? If it's very cold, so that's cold situation, and if you have very high frequencies, right, as we have seen before, but take care, you could also have influence due to the atmosphere. But if you go to 10 gigahertz, which is an X-band system, it's quite well. You can get total reflection at the surface, as we said, if you have very high temperature and it's very moist on the top, and you get volume scattering when the temperature is low. This is important. And if you're, if you have a decent, good, high frequencies, as you see here, and a decent depths also, right? If you have a very shallow, snowpack, only 50 centimeter or 30 centimeter, which we have normally also in cities, then you would see probably much more the ground and not really the volume, right? Because you need a kind of amount of volume to be also sensitive to the volume. Okay, there are different approaches how you can deal in order to characterize snowpack or volume, so snow in general, snow volumes. So the one is you use kind of a multipath coherent decay, which means you look for temporal decorrelation over time. So this is what you can do. And then you see when you have snowfall, the interferometric coherence is in principle dropping down because you have a change between two conditions, so 2 times, and the same is also happening in principle when it's melting. So like this, you could have a sensitivity to the interferometric coherence in terms of temporal decorrelation. You can also use single pass interferometry. For single pass interferometry, you have learned already what you can do. You can derive a digital elevation model, for example. This is something that you can do. And then you can use the digital elevation model here, the DEM, and you do just as separations. You do a digital elevation model for one time, and then 11 days later, probably a second one, and then again 22 days, a third one, and then you can subtract the height information from each other, and like this you can also get in principle information content about the snow. This has been done over, let me say, deep firm, but also in order to estimate glacial mass balances. Then you can use pure DINSER without baseline, right? Just with the same configuration. So what you do, you have an interferogram between two time steps with exactly the same configuration, no baseline, right, between, just the same. And here what you can do, you can see the movement on the ground, right? And the movement on the ground is depending on the soil moisture. That is not the movement in terms of the Earth's movement, but it's a movement because the moisture is changing of the ground. And so you get different propagation into the soil if you have a wet soil, or if it's a dry soil, or if it's a frozen soil. And this is something that you can also observe, actually. You can see the freezing and thawing, let me say, of the ground. This has been used quite often also in permafrost areas, let me say, and also for other things. And what I would do today is not all of them, so I'm purely going into polarimetry and really reduced amount of polarimetry to see or to show you that you can also still do something in this domain. And I'm going in principle to estimate this polarimetric phase difference, which is a copol phase. So let us see what is a copol phase difference. Probably just to say, so the copol phase difference is based on the assumption that the different polarization are penetrating or propagating differently into the media snow, because they are reacting differently with the crystals in the snowpack. And this is a little bit seen here. You see, we have here wavelengths, so lambda h or lambda v, which are in principle differently propagating through the snow because they are sensitive differently to the structure of the snow, to the crystals in the snow itself. And therefore, you have a difference between HH and VV, and like this, you could do, in principle, a difference measure between this polarization channel. So how to, oh, sorry, it's the wrong direction. What is a copolar phase difference? You see it, you saw already some of them. I'm just repeating a little bit what you saw already, what Alberto was explaining on Tuesday. So what we have for the very original signal, we have a scattering matrix, and within the scattering matrix we have 4 elements, which are our main polarization elements. So we are transmitting in HH and receiving in HH, or transmitting in VV and receiving in V, or doing a combination, transmitting H, receiving V, or opposite, transmitting V and receiving H. So like this, you can build up this 4 or 2-dimensional complex Sinclair matrix that you see here. And out of the Sinclair matrix, you can derive, in principle, a scattering vector. It's actually the same information content. It's just that you rewrite them in a different position. XX means that HV and VH are the same because we have this reciprocity theorem, which means in a monostatic case, these two observables are not different from each other. It's different if you have a bistatic system, then you would have 1 parameter more to account for, because due to the bistatic angle, you have different viewing direction, therefore your HV and VH is different. Okay, this you have seen already. It's a lexicographical representation, and out of this lexicographical representation, you can build up your covariance matrix, right? The covariance matrix is built up using 2 of these lexicographical scattering vector by the conjugate of the other one. And then you retrieve, actually, because we have a 3-dimensional vector, you have also a 3-dimensional matrix. So you, in principle, increase the 2-dimensional matrix to the 3-dimensional. That's the main idea behind, because what you like to see here, this is very good if you would like to see point scatterers. So you can very well describe with a Sinclair matrix a point scatterer. But if you like to see what are the depolarization, so the correlation between the polarization channels, then you would go more to a three-dimensional one, because here you have, in principle, the diagonals. These are the same as in the vector, or is the same also as in the Sinclair matrix. But if you go to the off-diagonal parts, like here, these three one, then these are in principle the correlation between the different channels, right? This is very interesting because you have then a correlation between HH and VV. You see it here, for example, or you have a correlation between HH and HV, which is then in principle here, right? So these are the correlation channels between these ones. And they're complex, so that's also different. So we have something which we can correlate, and that's actually the copol phase difference. What we do, we just take one of these correlations, yeah, and this is a complex number. We take this correlation here, either this one or these. It's because by definition it's Hermitian positive semi-definite. It means that in principle all of these values are positive, which means in these part they are equal. So therefore we're only counting in principle these part here, but these three here of diagonals are the same as on the other side. Okay, you can rewrite these also here in terms of CPD, as you see here. So this is how you would compute it with an arctang in the imaginary part and the real part. And this is in principle the definition of the copol phase. Okay, let us go a little bit in summary. I'm talking here about coherence. So it's a copol coherence in principle, what I will show you. So we have different types of coherences. At least this is what you have heard this week. So let me say you have heard about the pulsar coherence is something that I introduced now. I'm not sure if Alberto was saying this. And the insar coherence you know already, right? This is between two images. You derive in principle the interferometric coherences, so image 1 and image 2 in one polarization channel. And like this you see what is a relation between both, right? So it provides you a lot of information content in terms of how stable is also your interferometric phase, how accurate it is. In principle, a very good measure of a quantitative measure on how good is your interferometric phase that you estimate. So you like to have high coherences in order to have a very good estimate of the phase and a low standard deviation of the phase itself. And then you have heard also about this Pol-INSAR yesterday. What you do here, you combine actually interferometry with porometry, where you use in principle the scatterometrics observables, and then you correlate them in terms of polarization diversity. So it's the same, it's only what you introduce, it's more polarization diversity. Okay, and today I'm sticking more in this part where I'm using not interferometry, so the absolute phase, which is in principle the distance, right, between the object and the satellite or the airborne system. But what I'm doing, I use the relative phase. So relative phase means the phase between the polarization channels. So that's a little bit different because it's not as said, the absolute phase for distance measure, but it's a phase between the polarization channels. And also here you can do, we call this parametric coherences. Also here you do, again, it's also complex, relative. You take the channel, for example, HH and VV, and you do in principle, you can build up a coherence, which is the same value between 0 and 1, right? You can have, again, also same range, and you see if you have high coherence, you see then you have in principle very good estimate, or you have very close relation between HH and VV, but if you have very low coherence, you have a strong difference between both. So that like this, it's a very good measure also to estimate a little bit the parameters. So I will take data from TerraSat TandemX. This is it's a radar satellite mission from the German Aerospace Center, where I'm also doing the science coordination there. So if you like to have some data, actually also from X-band data, from TandemX, so you can go to the website and you can order some data. It's not so easy as with ESA's website, because for us, because it's a national mission, you need also to write a short proposal, but there's also data for free available. Okay, it's X-band. We are here in around 10 gigahertz, which is interesting. We have higher spatial resolutions as with the Sentinel or Biomass. So the wavelength is 3 centimeter, resolution is around 3 meter, and we have a repeat pass time of 11 days. Okay, that's how it works. a little bit. So we have 2 satellites. It means they are in this single pass configuration, so they can, in principle, acquire data in one spot, which means you do an interferogram at one time, and then you can do repeated a second single interferogram in one time, but you can also do the repeat pass. So that's a very, very nice concept. However, we have these kind of data sets. We are starting, clear, we have a synthetic aperture radar, and then in principle you can derive your radar backscattering intensities in all polarizations, possibly. In the moment, we are more focused in dual, so quad-pol is more, has been more a phase where we have acquired this data, because it requires much more resources to do it in quad-pol, so therefore we have done only kind of a 2-year phase to acquire quad-pol data, but in principle, mainly the main operation is in dual pol. You can also have single pol, but this is just to explain this. Okay, you can also go to more complex estimates, as for example, not only radar backscatter intensity, but you can also use the single low complex data, SLCs as we call them. And here we have 2 streams, the interferometric stream, where you can do, as said, the multi-pass interferometry or the single-pass interferometry, deriving a DEM or doing DE-INSA, if you like. And the other pass is using parametric phase differences. And this is, in principle, what I will do today. So we are focusing on this one. Okay, how we are acquiring this data. So we have different polarization modes, imaging modes. You can do single polarization mode with transmitting. So in principle, what you see here is always the transmission on the upper line. You transmit H and you receive H. So this was a single one. Or you do the switch then and you transmit V and receive V. In our case, what we do here now, we're doing a dual polarization. We transmit here, in this case, H and receive H and receive V, and then we transmit again H and receive H in this case. You can do it also, as said, in this quad-pol mode, but then it would be you transmit one polarization and you receive both one. But we are not going in this direction today. What is the price to be paid between dual pol and quad-pol? There's a price to be paid, and I'd like just shortly to tell you which one this is. I'm not sure if you're aware about it. It's in principle the swath width that you have, right? That's a little bit, in the moment, still a problem, because this has something to do with the transmit and receive part. So what is happening, normally you have a satellite and you acquire data over certain swaths, right? A certain area that you see here. And how does it work? You have a transmit signal, so you transmit from the satellite, you signal, and then you let open, in principle, your system to receive all the let me say, all the pixels in range, right? This is what you do normally. And then you stop, so you have a time where you stop it, and then you start again to transmit, and you let it again open to receive all the data you like, and then you stop again you switch always, in principle, you toggle between transmission and reception. And this is, in principle, associated to a time. It's called PRF, is repetition time. What is it? P? Sorry, I forgot. Pulse. Sorry, yeah, pulse repetition frequency. Sorry, yes, that's pulse repetition frequency. And this is quite, let me say, long or low in this case when you have a single polarization. And this actually is what you do when you, this is actually what you do when you have a quad-pol. Just to this main concept behind this, you have a transmission and receiver here, and you toggle between transmission and reception. And when you have in principle, transmission, you have an H, and then you receive in V and H. And then in the same, you toggle quite fast, you have a V, and you obtain V and H, actually. And like this, you can build up your scattering matrix. So you transmit H and you receive H and V, and you get, in principle, these 2 combinations of polarization channel, the HH and VH. And if you transmit the V here, then you can obtain again H and V, and you get the other kind of sets of elements, which is HV and VV. So that's in principle how it works. However, if you have now, let me say, so this would be in principle a dual pol system. So you have low PRF, pulse repetition frequencies. And if you have, you would have a reduced set if you have quad pol polarimetry, so this would be reduced because then the time is shrinking here in terms of to have a reception. And like this, if the time is shrinking in the reception, you see here, then also your swath width is in principle reduced by half of the width. So that's a little bit a problem. If you like really to do with the normal techniques today, so that's still a problem. There's now new techniques ongoing. We call it digital beamforming. And this is a little bit improving the situation, but you have always this kind of trade-off, actually. Okay, there is in principle, this is a trade-off to be paid. And here it's just, again, that you see what is the difference, actually, if you have the dual pole or the quad pole, as said, in the PRF is changing in principle, and therefore also your swath width is changing. Okay, what you could do now, you have heard a lot of nice application area, not application area, but you have, oh, sorry, I need to take the microphone, but I'm getting warm now, sorry. Okay. So you could, in principle, do the same. So for quad polarimetry, what you have learned is actually, oh, I do it here, sorry. That's here. You have learned that what we do is we build up these coherences matrices that you have seen already. And this is the three-dimensional coherency matrix that I was showing already before. But what you can do now, if you have only dual, so only two channels, you can also build up a matrix, right? You can also see what is the correlation between the two parametric channels, right? Now you have only two, not three. And you can also do a matrix. And this is quite interesting. So you build up a two-dimensional. So this is the three-dimensional, the things that you have learned about. And this is a two-dimensional one, which means you reduce your scattering vector to two dimensions. Now it's only HH and VV, or you take only HH and HV, or VV, VH, right? These are the combination that you can do potentially. And you do the same things, right? You do an outer product out of these two matrices. You see it here. And you get also a two-dimensional matrix here. Let us call it M or however. So then, in principle, these are the polarization channel that you have selected is A and B, and then you have, in principle, the correlation here. These are the correlation between A and B. You have this correlation coefficient, which is providing you information of how strong A and B are correlated. And you can play now a game. You can have different cases. You can have cases where you transmit H and you receive H and V. So then you would have these two channels, your HH, HV. Or you can have a different case where you would, in principle, receive the parametric channels in VV and HV, so here. Or you can even do now HH and VV. So let us have a look, how does it look like? What kind of information content do we get if we reduce the amount of our scattering matrix to a small one and have these kind of different combinations? So this is now the display of a normal area. It's an urban area with a small urbanized, but you have also forest, at some agriculture parts. You see also the blue. This is a Pauli composite of a fully parametric data set. Actually, the blue parts you know already. These are surface scattering areas, dihedral scattering areas, and the green one are more vegetated areas, right? You see it quite well. And now let us go, what is this correlation channel, right? The correlation channel, let us look between HH and VH, and you see this is a coherence, right? Remember, coherence is between 0 and 1, and if it's low coherence, as you see it here, then you have a very strong difference between HH and VV. You have no correlation, and which means also, what does it mean? How does your phase look like then, if your coherence is low? How does the phase should look like if a coherence is low? Sorry? Random. Yes, right. It's completely random, and that's a problem, right? Because you can't really estimate very well, let me say, the information content. If it's high standard variation, then you have a problem. And the same is also if you look now to these. So these we call co-cross, and this is then the other one. It's VV, HV is auch co-cross. You see you have some of high coherent parts, but these are more man-made structures, right? I would consider this as man-made structure, not really the natural targets that you see here. But if you go now to this HH, VV, it seems they have a higher coherence over some of the areas. For example, very nicely seen over this bluish area, which are the surface scattering areas. Some of these here, probably because it seems a little bit topographic variation. So also here you see some of these higher And yeah, and some of the forest parts are also higher. It's a little bit different, right? But this, you get much more coherence, much more information content. Let me say also in the phase, if you use the combination HH and VV, so the copoles, not the co-cross, but the copoles. So therefore, also this is a parameter why we choose it also for further investigation for snow parameter estimation. Okay, which means now what is happening here, even though you can do these combinations, right, between HH and HV here, so you would have a correlation coefficient between these two channels, it means in principle you have no information content here because you have no correlation, right? It's very, very low correlation, except if you like to do, let me say, some estimation or probably separation between point scatterers. So that's 0 and here's 0. The only thing is in this case where you have really a higher coherence and you can use it for any kind of information content extraction. So that you see already, it's important to choose the right combination in order also to increase the information content. That's in principle the message here. And what you can do further on, and this is what you have learned also, is you use in principle now either the coherence or the covariance matrix. This is independent of it. You can again do in principle it's a three-dimensional part, and what you do here is a diagonalization. So it means that you extract the eigenvalues and eigenvectors, and this is what you have learned on Tuesday. So that's the eigenvalues. You sort the eigenvalues, and then you have here also the eigenvectors. You also have a sorting of the eigenvectors. Remember, the eigenvalues provide you information a little bit about the intensity, right? You could imagine you have a vector, for example, and these could be, the eigenvalue could be the length of the vector, right? It's the length of the vector. And the eigenvectors are actually the position of the vector. It's your polarization diversity. So this is how you could, in principle, imagine what you get. And then, again, as said, so we are sorting the eigenvalues, and we are also, in principle, averaging, making a mean out of the eigenvalues because of the eigenvectors, and because the eigenvectors can be also written down as unitary vector with the 5 angles that you have heard already. And we use now statistics. In principle, it's nothing else as using statistical measures. So we extracting out of the eigenvalues the entropy and the isotropy. There's a statistic parameters, measures out of it, and out of the eigenvectors, we in principle deriving the alpha angle, which provides us the information content about which kind of scatterer do I have. So the alpha angle tells you which kind of scatterer, and the entropy tells you how many scatterers, if you like to imagine this a little bit better. Okay, but now we have only a two-dimensional vector, as we have seen before, only 2 polarizations, and we know already which combination we like to choose. So what you can do is actually exactly the same, right? You can except that you do 3, you do this now with 2 elements inside the vector, so it's a 2-dimensional matrix. You do also a diagonalization of the matrix, and then you retrieve again the eigenvalues, the eigenvectors, and you can do also derive in principle the parameters, the statistical parameters. For sure, these parameters will not have completely the same information content than the whole photoperimetric matrix, because you have more measurables there, right? So the statistics is a little bit reduced, or the information content is reduced, but still you can see the one is more responsible for information content randomness, which is the same for entropy. So it's increasing the randomness means increasing the amount of scattering contributions. Or here in this case, you are limited to 2 scattering mechanisms. So because you have only a 2 scattering, 2-dimensional vectors. Okay, let us have a look what is the difference between full pol and the reduced amount of scatterers. This you can see here. That's an X-band image taken by a Japanese airborne system here in fully parametric data over the city in Japan, which is called Gifu. They have here a lot of dihedral scatter. You see it already. This is a Pauli image, and this is in principle kind of vegetated areas. And you see also here river system is more bluish than here of these flat plains. Okay, here on top, this is what you saw already. This is a 2-dimensional representation between the alpha angle and the entropy. Do you remember entropy is the scattering contributions. So if you have low entropy, only one dominant scatterer. If you have high entropy, 3 dominant scatterers. If you have alpha angle, low alpha angle, it means you have surface scattering. Medium is more this volume dipole scattering. And if you go up, it's a dihedral scattering, right? So that's in principle the category. And this is now each pixel taking out of this image and just plotting it in this 2-dimensional plane. And what you see now here is these different dual pole cases where you transmit H, transmit V, or have H, and VV, the copole, right? And you see already what kind of difference you get just from the image perspectives or visual look on this one, because we see we have quite a lot of dihedral. So we have here quite so high alpha angle, quite dihedral. We have a lot of greenish areas, so also high entropy here in the middle part and lower here because we do not have so many areas which are really low scattering areas, right? This is what is represented by this image. But now if you do only the reduced set, the co-cross part with H or the co-cross part with VV, you have a limited amount of information content. Whereas when you use now the dual copoles, it's not the same, right? I would not say it's the same, but you increase a little bit the amount of information content, which is improving in principle later on as you estimate. Okay, you can play now this game with different objects. So as I said, you can do it with GIFO. Now this is a different area, therefore, or different display. Therefore, I was putting, it's a different 2-dimensional image between alpha and entropy. But if you do, for example, an Arctic ice cap, you get this one. You see it's a very, very focused information content, so very much like it is a volume scattering, mainly what you have here, and therefore it's high entropy and medium alpha, so that's very particular. Then you have your very difficult terrain. It's a mountain area. Argentière is a glacier in France, and you see you have everything from really surface scattering going up to volume scattering because it's over the glacier here. And it's a rural area in Germany, in northern Germany, where you have also quite a different particular shape, let me say, of this entropy alpha. This means you can play around a little bit with them in order to detect probably different features or be sensitive to different responses using this two-polarization. Okay, this was a little bit the introductory. I was going back to snow because this is what I promised to do today with you. So what you see here now, I'm focusing on the Aletsch Glacier. It's clear the Aletsch Glacier is one of the biggest glaciers, I would say still in Switzerland. I'm not sure whole of the Alps, but at least in Switzerland. It has a length of 23 kilometers. It's very high located and has a research station. Therefore, it's a very great area here on top of it's on the Jungfraujoch. It has a huge research station where researchers can go there and put their instruments, which is very nice. So we have done it also quite several times. It's really great. And, but however, as all glaciers, also this glacier here is in principle retreating in terms of mass quite strongly over the years, so up to 4 meters a year. So it's quite, quite essential. So this is Switzerland. You see here Switzerland, and the Aletsch Glacier is in principle here. So we have collected data over several years of tandem X, this time series in this dual pole between, even now we are still collecting this, but what I'm showing is this 7-year time period, but I take 2 samples out, 2 years, so that you see a little bit the differences. Yes, as said, the spatial resolution is quite high. It's a little bit different as what you have with Sentinel, and this in principle is to tell you what we're doing. We're doing a whole series over the year, which is interesting because we like to see the changes of the snow when you have snow precipitation, or precipitation in terms of snowfall, but also melting ongoing. Okay, yeah, there's an image on this upper part. Probably just go back. The upper part of the glacier, of the glacier is this one. This is the Concordia place here, where all the glacier arms are floating together. And this is in principle this place here. You see that's a huge area, and here that's one arm. This is where Jungfraujoch station is, and these are the 2 other arms which are coming here into this main area and then floating down in this direction. Okay, let us have a look on the time series now of the data itself of the Aletsch Glacier in X-band. here in this TerraSAR X image. And what is already interesting, you see, I mean, you see what is very nice, you see the glaciers here around, right? And it has, in November, quite good, let me say, signal, right? What you see here is in principle the radar backscattering signal. And this radar backscattering signal, when you go now over time, this December, January still high. It's a little bit changing here in the middle. March, you see, here's also March. But then in April, you see it's getting darker, darker, and even darker, right? Very, very dark. So you have changes in terms of radar backscattering intensities over the time. So this is what you see here. And this is now only in one polarization, which is HH. Let us have a look on what is happening, why we have a change of radar backscattering intensities. So in principle, we have two conditions. We have a winter condition and a summer condition. In the winter condition, you have seen we have high scattering ongoing because what we have is we in principle penetrate right into the volume, and then you get volume scattering, which is much stronger. And if it's in summer melting, so the upper part is melting, so you have a little bit of water, small thin water layer on top. And what is happening here, you have a lot of forward scattering, so away from the sensor. So therefore, everything what is coming very, very low signal back to the sensor, and therefore, in principle, you have this dark appearance of it. And you see this also then now in entropy, in the entropy. So this is really a dual pole entropy, what you see here. You see it also in the entropy. You see it can be different also for the arms. So here you have a higher entropy, so more scattering ongoing, more scatters ongoing. But here you see, in principle, also a variation. So in principle, between winter and summer. So in summer, in winter, sorry, a lot of scattering ongoing, and in winter, in summer, sorry, less scattering ongoing. So therefore, you have a less amount of lower entropy. And with alpha, you see also here the alpha is higher, which means I have here volume scattering mainly, also dihedral scattering with the red part. And here you see it's blue, and blue means I have more surface scattering, which makes sense, right? Because if you have forward scattering, you would have more surface scattering coming back and you're not penetrating, so you don't have really volume contribution. What you see here is just, in principle, a digital elevation model, which is representing the heights that you can see. Okay, let us think. So scattering mechanism vary with snow and ice conditions. I mean, that's important. This is what we see. But even within the single scene, so you see differences, right, within spatial differences on the glacier itself, so that's important. Okay, what you can then also do, I mean, you can not do it for winter, just one scene, but you can also look here for the whole time series, actually, to have an observation. And what is interesting with this dual pole, you can really see quite well also how something starts to change much better as using only the intensity. So you see in principle in August here we have still surface scattering, and then in September it's becoming already at this height a little bit, let me say, colder, right? We have a principle in metamorphism of the snow, and then what is happening, you have the first snowfall, mainly in November it starts to have the snowfall, and therefore these arms seems also always to be already more affected because actually it's even higher located than the other arms, so it's even higher. So it means that the change in terms of temperature and the change of the snow is also varying stronger. And then you see this is happening over the whole glacier, so you have also everywhere snowfall in January, the same is in February, quite interestingly. And then you start, in March, you start again getting warmer. And you see it already that the lower part starts first always, right? Because it's lower, it's heating up, and you have a change in terms of the snow conditions. And then it's becoming more and more bluish on the lower part. You see it here already. And then it starts also to be in the upper part here. For example, April, May, you have a strong transition where you have a lot of, let me say, the entropy decreases here strongly in the upper part. You could also still have some snow, let me say, snowfall still also in May, and this is what you see here between these two parts, right? You see that this becomes again more, the entropy is again increasing, and you see actually that between this time and this time, you have again a kind of a snowfall and therefore accumulation. But then from May to June, it's again in principle melting ongoing, and therefore you have surface scattering as you see here. So that's in principle very well can be followed, actually, this line. The same is for the alpha angle. So you not only change the amount of scattering mechanism, but you also change the type of the scattering mechanism. And this is what you see here. You're coming actually from surface scattering here until volume scattering, which is greenish, and then dihedral scattering, which is reddish, right? This is very strongly seen also in February, very, very strongly. And in March, it starts again to melt, as same as we have seen before. We had still a snowfall here in April, if you remember, so therefore more affected by the higher area quite strongly, but then really slowly, or even, sorry, it was in May, here you see it quite strongly, and then, but from June you see it's only surface scattering. So it means really we have strong melting ongoing. Okay, so let us a little bit see what are the basics, a little bit of a glacier, how a glacier could look like. So we have in principle two main parts, which we called ablation or accumulation zones on a glacier. The ablation zones are the zones where we have permanent melting ongoing. So this means even if you have a snow cover in winter, these snow covers actually closely, totally melted in summer, and then you only have the pure ice beneath. Whereas in the accumulation zone, you have snow falling, and then you have a transition zone, which you call firn area. And then the firn area means, so it's not completely melted everything, but the snow is transforming to a denser medium, which is firn, and this denser medium stays in and becomes ice after a while, right? If you have more and more accumulation ongoing, then this is pushed down and down. It's more pressure on it, more density. So the density is changing, the crystals are changing, and what you have here, you see it already, it's more, you have more lenses inside, so more structure, I would say, in these ice firn parts here. So which means here we have in summer pure ice, and here we have still snow and let me say compacted snow, which we call then firn. So this is a little bit the difference. And we have, and then, I mean, you have a borderline between these two situations or conditions, these two zones, and they're called equilibrium line, which is in principle the balance between more melting ongoing in terms of then having also accumulation. Okay, and what we have done, we separated these two zones. We were saying that in principle, the accumulation zone is the upper part of the arms of the glacier, and the lower part is the ablation zone, which is total melting ongoing. And then if you just have a look now over the time, this is a sigma 0, so radar backscattering intensity, then you see now the red one is for the ablation zone, and the accumulation zone is the one where we are still accumulating and more snow. And you see they have a difference in terms of signal strength over the time. This we see quite constantly. We have here an interaction when it's becoming really melting ongoing very strongly, and this reversing, but however, they are following, however, quite nicely the same, I would say, the same trend over the time. If you now look for entropy and the alpha angle, we can also do here this separation just to see what is different. Between entropy, the accumulation and ablation zone are closer together and are also following a line, we can see, and have the same trend, right? And also having here the same trend where we have the bump in terms of melting ongoing, or even we saw here in May, remember it was also again a snowfall, so therefore we have here also this bump. And for the alpha, so this again only the amount of scattering, so the entropy and which type of scatterers is the alpha angle. Here we see also quite interestingly in November, also these two parts are a little bit deviating, the same as here. In the beginning they're quite close together, right, when you have the melting period still, so still not so much snow, but let me say the area of where you have in principle a thin water film on top, then both react in principle same, right? You have the same kind of condition. The same is also for entropy as well as for alpha. So you don't have a separation of the scattering contribution here really. But then in this, when we increase in principle the accumulation, so when it becoming colder, you change in principle your scattering mechanism. So therefore the alpha angle is changing in terms of time. However, the differences are between accumulation zone and an ablation zone is not so different, right? We have the same trend, but the levels are a little bit different. Okay, what you could also have then a look, so this was within one time, so 1 year. You could also have a look now between the years. So this is because we collected data over several years. What you see here now is a sigma 0 in HH over the years. So this is from 2011 going until 2017. And then for different months. And what you see is quite interesting. So you have a little bit, it's not a continuous line because we have measurements which are missing in between. So therefore, all the bigger dots here are in principle our measurements, and then the holes are when it's connecting the lines here, right? So this is what you see. However, you see it also here in the ablation zone. It's in principle the bluish one, and I would say the violet line is in principle the accumulation zone. You see also here some differences over time, but what is interesting, this is within the year always, the red box. So you see you have, within the year, you have a change, right? Because this is what we also see in the signal, you have a change actually because of the variation between melting and snowfall, right? So this is always this variation and the seasonal variation, but then this is again, that's in principle then the winter, no, this is a summer period, this is a winter period, and you see the difference, right? It's going up in the high in principle in terms of signals. You have very, very high signals when you're here in principle in this winter period, and then if you go to the summer period, you have a low signals. And this you can actually see, in this year we only had one value, right? This is very difficult to see, but in times where we have more acquisitions, you could see it quite well actually. So that's, we have a seasonal variation quite strongly. Okay, the same is also visible when with entropy, you can see it quite nicely, but also with the alpha angle, just to see. You can also do this over the years, and you can check if you have some differences in terms of scattering mechanisms. Okay, let us go now to the HH-VV or the VV-HH parametric phase difference. This is now only using HH and VV, not doing really now the diagonalization of the two-dimensional scattering vectors, but really only one part of the coherency matrix or covariance matrix. And what you see here again are colors, so probably just to mention, so everything that is green means in principle you have no phase difference. So what you see is here the phase, so when the phase is coded between minus 180 to plus 180 degrees, so this is a phase that is have this 360 degrees phase cycle, and everything that is green is zero phase, which means we have no change between H and V, so there's no difference, right? But if you have in principle here bluish colors or yellow reddish colors, you have a strong phase difference between these two channels. And if you start now, again, we know already that in August we have melting ongoing, right? We have mainly surface scattering, and what is interesting here it's quite greenish, which means we have not such strong difference between HH and VV. So the variation, the phase variation is quite small. However, if it's becoming colder and we have accumulation of snow, you see already here in the arms, this is a first start, we're becoming more bluish. And then over the whole part here in December, it's becoming everything bluish. It means we have a stronger phase difference between HH and VV. And you see it also spatially, it's quite diverse, right? Quite different. And it's become even also negative in this part, which is becoming reddish. So you can have really a kind of a phase wrap, right? Where you, in principle, you become very, very dark violet, and then you wrap, in principle, to minus 100 degrees. So this is what you could also see here. So you can have two parts. So that's in January, February, and then when you see when again we have less penetration, right? This is also connected to less penetration. Then, in principle, it's becoming again greenish, which means green in the lower part first and then later in the upper part, which means again we have no difference, phase difference between HH and VV. So like this, we see that this VV and HH is quite sensitive to changes in terms of snow properties, but also changes in terms of how much we can penetrate, right? Before we have a lot of surface scattering, which means we are not penetrating in it, but if you have volume scattering, which we have seen with alpha, you can penetrate then. You can also see it very well here in this HHVV. We have a strong phase difference. Okay, so why is now this parameter, let me say, related to snow depths? Because I promised that what we do with the copol phase or the CPD is to estimate snow depths. And there's several studies have been reported in order to report in principle this snow depth estimation or the sensitivity to snow depth. So one is in the very 1996, you can see here, where an experiment has been done using very high frequent data, so 95 gigahertz, for example, here. And they have observed very high phase differences. You see here, so that's a phase difference here on this part. I think this is the incidence angle, and this is in principle the gigahertz, so very high frequent data. And you see here a very, very high bump in terms of phase differences when fresh snow, or even, oh, sorry, probably this is also degree day, could be, sorry, that's a time, it's not an incidence, it's a time. And you see here fresh snow was falling, and therefore you have a very strong change. And you have seen it already before, also on the Aletsch Glacier, that when we have more melting ongoing or surface scattering, we have low separation between HH and VV. They are very close to each other, so we have zero phase. But then when the snowfall comes, and you see it here, we have a very strong phase difference. So that's one observation that has been done. And later on in this part here from Cloud in 2000 or Parella 2013, 2016, there we had the first time we were checking what is so to try to model this a little bit, to have an understanding why is there a relation between phase difference in HH and VV to the depths of the snow. So this has been in principle provided here a little bit to play also around with the crystal structure, because you can imagine, like in forest, we were assuming in principle a random volume of a forest, right, sometimes, but you could also have oriented volumes. And therefore here they have played around a little bit with the oriented particles, not random particles in a snow layer, but kind of oriented. And this is something that I will show you then later on too. And for sure, what has been also observed in 2013 here from Riche is also what is happening, that you have a recrystallization, and then this has also strong impact actually on your, so in principle, the metamorphism, so the change of the grains structure in the snowpack, and this has in principle a very strong impact also to the phase change, which is associated actually to a temperature change also. This was also something that's very interesting, because it would be really cool, right, if you can, with depths, if you can make in principle, if you can use the snow depth estimation also as a temperature measurement instrument like this, if you can say. So therefore, this is also quite interesting. We haven't done this up to now, and it's very difficult to make reference data on it, but this is, I think, a very nice and very innovative idea. So how snow looks like, probably it's important to know this a little bit before you start to model it. What you see here on top is in principle representation from, I took it out of this publication from Riche, is in principle an image of a snow grain. So what you see here is an image of snow grains over certain, let me say, area. So that's in the, let me say, 10 millimeter scale here. And this is how snow looks like when you use very fresh snow and you do an image out of it. So on week 0, so very fresh fallen snow. And then you see the snow is starting to change in the same area if you don't have more accumulation, but it's the snow itself, the snow that was falling in week 0. So it's changing the crystals. And you know, even then after, let me 12 weeks, you have a completely different composition. It looks completely differently from the crystals in principle of these snow. So after 12 weeks here. So in principle, they call this change or metamorphism of the snow crystals recrystallization. Okay, what is happening actually, it's very difficult to really see it here out, but what is happening actually is here a simplified model. So what you assume in the beginning, you have very fluffy snowflakes, right, which are falling to the ground, and they are kind of layered then here, right? It becomes one kind of layering in one direction. And then when time is starting to change in principle, the wetness, but also the structure because of the shear strength, of the strength that you have on it, they become more flat. So there's not any more fluffy crystals, but more like discs or smaller dipoles, I would say. And then after 12 weeks, you see it here, they become a different orientation. So in principle, they are changing from horizontally being oriented when they fly, and when they, in principle, attend to the ground, to something that is more vertically extended. So that's very interesting. And you can try to model this. This is in this graph here. We have this HHVV phase difference here. And we try to model, in principle, this structure from a prolate to an oblate. So actually changing the axis of the crystals. And you see we have quite, for different incidence angle, you have a change in the phase here. So starting with 45 degrees, right, you have a quite strong change in terms of a negative part for prolates. And if you go to oblates, so the other one, then you would get positive phase differences, right? So that's the negative and positive part is also very interesting because you have different, you're in principle observing different situation conditions of in principle the snow pack and the crystals inside the snow. And the same is also true. This is in principle this crystal structure which makes an influence, but also what is influencing is the snow density. So how compact actually is the snow. And also here you see we have a change with the incidence angle from the satellite or even from the airborne system, that for low density it's less difference, but if you increase the density you have also stronger phase differences in HH and VV. Okay, yes, and out of these the idea was now to, if you know these, right, that in principle the snow is changing or having this metamorphism, in time, then you need actually also to adapt your model and to try to model it perfectly. And what we try to do is to put some assumption in the model in order to have, in principle, a right model to, or a simplified model which is accounting for it. So in principle, the main idea was to have a kind of a two-phase mixture, which means we have an interface between air and ice. That's important. Then we were integrating, in principle, it's called degree of anisotropy, which means the shape here of how the crystal looks like. So that's in principle our degree of anisotropy. And then we also integrated in principle the permittivity, so effective permittivity, which is here counting for the degree of anisotropy, but also in terms of density. So that's also important. And in the end, what we also need to account for is the refraction, which means if you propagate into a volume, then you have a different scattering contribution also within the volume. I show you this a little bit here on this graph. What you see is, in principle, you have here a satellite, you have your incidence angle range, right? Here in incidence angle, a certain incidence angle, but then when you approach this air snow interface, then you have a refraction here, so a different scattering, right, with the different angles in this part, which is then the part of the snowpack itself. And what we have tried to do, we have modeled quite simply this HHVV contribution in terms of the depths, which is L here, of the snowpack, in terms of the wavelengths, you need to count for it, and then also in terms of the refraction, which is then differently for H and V component. And here you see it again. So the L is the thickness, is the wavelengths. Nu is in principle the refraction different for H polarization and for V polarization. And that's as a function of the degree of anisotropy, the density, and the incidence angle. Okay, if you have these, so the question is now, how does your sensitivity looks like in terms of using, in principle, here the HHVV phase. So if you change your wavelengths, because these have been the main parameter we've seen before, which are important for the model, you see that increasing, in principle, the wavelengths means also you increase the sensitivity, because the sensitivity is becoming much stronger here. The colored lines are in principle the different incidence angle that you can see is a little bit different depending on the incidence angle that you have here. You can also look what happens when you change the degree of anisotropy, right? This is the orientation and the shape of your crystal. And here in principle, it means that if you change the degree of anisotropy, you're becoming more sensitive, or you're more sensitive for higher anisotropies, which is here, because you're more separated actually in these areas. So here the values are very, very small, but here you have a higher separation, therefore you have a higher sensitivity here. And increasing, in principle, what happens when you have density of the snow, so increasing the density, you see you have in principle an increase until a medium dense part, and then in principle it becomes ambiguous because you are again going down, so it's in principle too dense to be accounted for. So you have a kind of limitation here. And for the thickness of the snow thickness, so this could be your relation. So if you have higher separation, so higher HHVV differences, right, then you see already, depending on the incidence angle, you get also more and more thickness. So you have very low separation, HHVV phase difference is 0, then you have no thickness, is clear, but when you increase the phase difference, then you also increase in principle quite linearly the thickness. So at least this is a very generalized model, right, which is modeling this relation. And like this, you can see now which parameter are really affecting the snow depth estimation. And this is important to understand. So therefore, I'm always saying it's important to see data and to understand the physics behind, which you try then to model. Okay, we had also make some ground measurements with a ground system, which is called SNOWSCAD. This is a test area here in Finland, in a forested area, and you see this called Sodankylä, and this is the region which is a snow region. That's a tower where the system is on top, and I'm just going now through it so that you see it. So there's a tower with a, I think it's a C-band system. I'm not sure if they have X-band. I think it's in the C-band, but we see it in the second now. I don't remember anymore. And what they do, they have 7 subsectors in terms of the azimuth samples, which they are calculating. They have also a little bit on forested area. You see it here in this section, but we were focusing now only on this snow part here. And that's, in principle, the different incidence angle that you can then get out of it between 30 and 60. And that's the corner reflector or sphere, which is calibrating in principle the data. So that's a radar sphere for calibration. And then there's a reference data station for water measurement. It's called Gamma Water Instrument, which is estimating the snow water equivalent, which is a sweep parameter. And then we have also, I mean, they have done some snow pits estimations. So they were digging in the snow and also estimating by hand SWE, or making taking snow measurement and in principle weighting the water column actually in grams. And what they have also is an automatic weather station here, which is measuring air temperature, precipitation, and also snow depth automatically. Okay, yeah, these actually originally has been built up. It's also an ESA project actually, has been funded by ESA for a mission which was called Core H2O, and it's a mission, it has been a mission proposal where they use 2 wavelengths, an X-band and a Ku band, in order to estimate with a difference of the frequency also snow water equivalent. But this mission was not successful, And yeah, it was just a proposition, but it was not going further on. Okay, now here you see the frequencies. Actually, it's really from X band, as you see, higher, so no C band, going to Ku band, as you see it here quite well. And what is interesting is the acquisition rate, which is 4 hours, so that's quite nice. So it's a good part to play with. So what we are doing now, we are doing kind of correlations. So what you see here is now a graph where we used, in principle, the measurements of TerraStar X, right? The 3 measurements over certain areas, and we were comparing them with the snow height, actually on the ground, and we get quite good correlations. I mean, you see still a kind of a variation, right? Because we have spatially quite differences. So that's the total snow height after 30 days, where we had already quite of metamorphism ongoing. You understood already that after months, the grains are changing, actually. What you see here is now the change of the phase. So what you see is just a phase difference, but you could do these with a change of the phase difference. So that's a change of the phase difference. Therefore, it's called CPD. And if you do the change against accumulated snow, you have even, I mean, you need to make an averaging a little bit over certain areas here, over bauxite, and then, but I think this is the main side, the open side, the bauxite was more outside, and then even this is, I think, the forest side. So we have some correlation, but not, but they are quite good, and this is a change after 11 days that you see here. And then what you could also do with the ground-based measurements that we had with the snow scud, so we have done also correlation between the snow scud. So that's in principle changes of snow height within 13 days. So temporal changes, and also here the changes using in principle the TerraStar X data. So it's quite interesting. So we have also looked in terms of time, how does it look like in terms of time. And you see here quite on top, these are the snow depths estimated by the measurement system, so by hand. You see soil temperature, that's a red curve, and this is the accumulated snow depth, which means what you see here, they started here in 2000, there's a time series between 2012 and 13, starting in October, where you have starting the first snow accumulating, going up, right, and then going down here in April, May, where we have, again, let me say, ongoing less snow and less snow as a precipitation, and therefore a lot of melting and high temperature. You see it also here low temperature, and then here plus temperature on these borders. This is TerraStar X, the estimation that you see, just a difference, the phase differences. And here this is a snow scud, which is also providing phase differences, but in a much, much higher time resolution, right? Here we have a time resolution of 4 hours, and here we have 11 days, right, if you remember well. And if you now check them, which is quite interesting, they have quite the same trend, right? If you look now here, no data has been acquired, so if you have a little bit of gap, but here you see we have data acquired, and they are quite following the trend of a satellite mission also, so that's interesting. That's, if you go zoom a little bit in terms of what sections do we see sections of snow accumulation, so snow that it was falling, and you see it here on the peaks of the ground measurements here quite well. So here there are the peaks, and you see also the peaks, let me say, in the satellite image, right? So that's interesting in this phase difference, and you see also probably a little bit shifted in time, but also the peaks here in the mainly on the ground-based radar system that you see too. So that's quite interesting. So you see when snow is falling, we have a strong change in terms of phase differences, which makes, in principle, it's sensitive to something that is changing in terms of the snow. And then you have also the other parts, which are more the melting parts or the settlements of the snow. So here you settle, so you have a metamorphism actually after a snowfall. So after a peak here, you have a settlement, and you see also it's changing. The snow depth is a little bit changing because the crystals are fluffy in the beginning, do you remember? And then they are settling down. They're becoming more kind of shaped of elongated, so they are settling down. And you see it also in this ground measured area, right? So therefore you have a plateau, a kind of plateau, and sometimes a little bit negative. And this is interesting. You see the settlement of or the metamorphism of the snow also in the radar data and the satellite data, because you have a bump when snow is falling, fresh snow, and then the metamorphism, you have a lower change or lower difference between the HH and VV polarization. And what is also interesting, you see it also in the snow scat, right? Here also it's very, very going down, also this bump here. And here we have still snow, right? It's still cold enough to have snow, but the snow settled and no fresh snow was coming, so it's just settled down. And you have in principle, therefore, this plateau. And here the decrease of the phase difference and also the decrease of phase difference also for the radar system. Yes?
And the peaks are delayed, right?
Yeah, they are a little bit delayed. I mean, yeah, because you mean mainly for the snow scat or for the tandem X? So both, actually. Yeah, both are delayed. Yes. Yeah, because you're normally not really acquiring. I mean, you acquire every 11 days, right? And probably you have a little bit. You don't have such a good sample for the satellites.
Snowcat every 4 hours, right?
Yeah, that's right. For snowcat, yes, and you see it also in snowcat, as I said before. Yeah, you have a little bit of delay. It seems it must be something to do with the structure, right, of these, in principle, of the snow itself, to really have this difference. In principle, it's a different propagation, right? What you have is a different propagation of H and V into the snow, and you're right, it's a kind of a small delay. It's not clear still physically what exactly it means, but yes, we also observe this. Okay, we have, so that's now, this has been the snow, in principle, the area of Sudankale, but we're coming back to the Aletsch Glacier, actually, right? And I'm using now, in principle, data from the Aletsch Glacier that you see here. So what you see here now is, in principle, also the time. So I was saying already before, we have the time, and you have here, in principle, a measurement of inverted and or measured, in principle, centimeter in terms of height of depths of the snow, snow parameters. So the inverted one are the one that has been model inverted, but the other one are the one that has been, in principle, measured for each time step, right? This is what you see here. You see the measured one because here is a measurement station on this point. It's a little bit far away from the glacier, and it's not on the glacier itself, right? It's a little bit on this mountain. That's a quite of steep mountain peak here, but we use it as a reference because there's no good reference otherwise where we could check this. So you see a little bit of variation, but at least we see sometimes when we have snow coming, it seems also that we have also inverted snow for the tandem X data. But how we are representing this better is to accumulate these acquisitions, and we are doing in principle a total snow height measurements, which is an accumulated version of the single estimate that you see below. Okay, let us still go how the copol phase looks like. So we see, or we know now that for fresh snow, what is happening, the HHVV is increasing, so it means the phase is increasing for fresh snow, which means this is related also then to an increase of the depths. And for low HHVV differences, so becoming more to zero, we see what is happening here, that we have a snow aging, right? This is what we have seen on the ground-based measurements, which means that not the length, so the depth is not changing in this case, right? We have still the same snow pack in terms of depths, but what is changing is in principle the age. So this needs to be accounted when you always look to this copol phase difference. Okay, what we have done now, as said, so we have this copol phase difference. We have the model that I was showing before, where we have the relation between the copol phase and the depths, and therefore, in principle, we have inverted then these relation here that you see to a snow depth. So therefore, you see here height now, and this is an accumulated version, as I was showing in the previous slide. And with the accumulated version, what you see now, so the bluish greenish lines here are the model predictions. So this is what the model is predicting, and the red one is in principle the measurement that we have. So for the model, we need to do assumptions. This is what we have said. We need to figure out what kind of density of snow do you have, what is the degree of anisotropy, and the wavelengths we know, right? So that's fine. So like this, we were changing a little bit the degree of anisotropy, so therefore this is for different model parameters, but we fixed in principle the density of the snow. But you can imagine the density of the snow is changing a little bit in time. However, this is now fixed, and even if you fix it, you see it quite nicely that you follow also the same trend as what we measure with the TerraSAR X satellite, actually. That's quite nice to see. So, and this is over the Aletsch Glacier, the estimation now. These are between 2016 and 17. You see here you have no snow difference, so height differences, because the phase was 0, but then you start to increase, right? You have here also increase of the copole phase, you increase it, and you see also the model is increasing. It's not so, let me say, has not this variability as, for example, the real measurements that we have, but it still provides you the same kind of amount of estimation. So you see you have a kind of plateau, you have some peaks here, which means we have some snow falling ongoing still here too, but then here it's kind of again a plateau in terms of snow accumulation. Okay, that's the air temperature, which is corresponding a little bit what we see also. So the model parameters seem, and the measurement that we see here are kind of corresponding. Here we have colder, here we have colder areas, and here too, but then here we become plus, and here's plus measurements, and this is still, here's becoming a little bit warmer, right? This is the area also where we have here the plateau is becoming a little bit warmer, and this is the area in principle where we have minus temperature. So also this is very important, right? If you like to check how much you penetrate and how much volume you see. Okay, here's still to say that's the plateau that we see. So we have becoming of warmer temperature in this region, and this is the area again where we have the peaks with the snow coming on top, right? So we have the snow accumulation on the glacier. And this can be now also done, can be done for different time steps. This is now for 2011 and 12, and before you have seen for 16 and 17, just to give you a little bit a different copole phase difference. And you see here we have a strong difference, and then it's a kind of plateau here again. And this we have transferred in the model in terms of snow height, and again tried to find parameters with different degree, so degree of anisotropy, which is in principle our shape, right, and orientation of the crystals that we changed in the same way as before, and the measurements that you see here. And again, you have the same thing, right? Again, also the measurements from the station in terms of temperature. You have here where you have these peaks, it's cold, right? It's below 0 quite a lot, and then here still, but then it's becoming warmer and warmer, and you see it also here already. Okay, again, this here becomes warmer, it's getting, the melting is ongoing, right? And you see it already then also, therefore you have here also the plateau, and you see it here too, right? The snow is, it's not only, here's the plateau because the snow is aging, right? But this is the same signal as if you would have melting ongoing, right? This is a little bit confusing. This needs to be taken care. But if you take then the model can say if it's really, let me say, the height, or if it's in this case can separate, or if melting is ongoing. So that's a good thing not to use also a physical model behind to understand it. And that's here, this is a region where we have compaction, and this is also related, so where the snow is settled down a little bit, right? This is this area where you have going down a little bit the signals, so the height is going down a little bit because you have a kind of a compaction. Right, sorry, going back. I was not showing, but you have also these peaks with the accumulation are the white areas then here. Okay, yeah, so let us go a little bit. That's a nice tool, right, to simplify or to use only two polarization, but still have an application and to do a physical parameter estimation using also model-based approach. But sure, there are limitations, right? And the limitation is clear. It's depending on the temperature of the snow and also on the air temperature very strongly. It's depending on the density, as said already. Probably the density is changing during time, but you have seen the sensitivity is still quite good. You could have rain in between, then everything is changing, right? Because if you have rain in between, then in principle you're becoming surface scattering, so you can't penetrate, and probably you would get a decrease of HH to VV, but this could be accounted as being settlements, right, settling down, but it's not. This needs also to be taken care. And also the mass of the snowpack is also important, because what we here assume that your snowpack actually is not larger than 2 or 3 meters, and you need a wavelength which is penetrating so deep so that you see also the snowpack. So therefore, either you change the wavelength or the frequency, or you to adapt to the amount of snowpack that you're considering to have on the ground. So that's also something that needs to be taken care. What can also happen, you can have snow drift, right? All these physical parameters which can also change. It must not change. It must not be then that you have a change in snow height, but it could be not due to accumulation. It could be also due to wind, right? That you have just a displacement of snow from one region to the other region. This can happen too. So which is changing also your density. As said, snow metamorphism is one part, right? It's not clear if we capture really with a simplified model all the different structures, for example, the delays, right? These small delays could be also something that could be accounted to it. And the snow compression is also, in terms of weight, could be also differently, right, as what we are here accounting for. Okay, why is snow important? I was not putting this in the beginning, but I mean, snow depth is one important parameter, but we have, as said, also snow water equivalent, which is in principle measuring the water. So if you melt snow, you in principle measure the weight of the water column, which is coming out of your snow. So this is SWE, snow water equivalent. And snow anisotropy is also very important in order to understand the structure. And as said, fresh snow depth is also important. This is important for all of different kind of relations, for hydrology, runoff, also for water availability, for vegetation, in general for the climate, and for droughts, risk management in terms of flooding also, but also avalanches, and any kind of different things, but also for, in principle, for all the animals that are also outside, they need also in principle these kind of, they need also snow and the cold, and clearly also traffic information. Okay, I was stopping now here in terms of showing you a little bit what you could do with the parameters, and I have now just one example, still the last 15 minutes, probably a little bit less, in terms of biomass, because what you will do later on today, right, you will have a look on biomass data. And mostly you can also use other data. I was saying this already to some of the groups, that you can also use other data, but biomass is great because you can play with polarizations very well. But for the other data you need, for example, for TandemX, it takes a little bit a while to download them. So this is probably not recommended now. So therefore just use biomass, and you can also apply in principle this coherence difference, so the phase difference in HHVV also to biomass data. Just to come back, so biomass is much, much longer as what you have seen now for snow, right? We're penetrating much deeper into snowpack and getting also information about ice content, so that's really interesting. And why P-band is also great for this kind of cryospheric application is that you get also you get scattering from layers, right? You get scattering when you have kind of melt layers in the ice pack, so that's very great. And like this, you can get more information about the layering of an ice cube. So I would not say that P-band is really only sensitive to snow, but it's even penetrating deeper as snow. But it's very depending. So we had, probably can say we had measurements like in Greenland, where we were penetrating up to 20 to 40 meters, but then we had different areas in Greenland where we were penetrating up to 80 meters, right? So it's really depending on the region and how much layers you have actually in your snowpack or ice pack. If you have more layers, you have more scattering ongoing, and you're not penetrating really much deeper. So that's a little bit the point. Okay, so that's biomass acquisitions. This is a Pauli scattering vectors that you see here, the Pauli representations, again with the different colors. That's an area that has been covered during the Calval phase now. And these are available also on the server, so you can just check out and look to them. So what is interesting here, if you look just to the Pauli RGBs, what is interesting, you can see this part here, which is a glacier part, right? You see really great floating glaciers, which is very, very bright. You see some structure and different Pauli RGB representation in this upper part, which is more mountain areas here. And you see these very reddish parts, which is more in the inner part of Antarctica, where you see also quite of different structures. So that's very generalized. I will zoom in now in one of the scenes that you can have a look. So this could be my project. I could present this as my project today, if you like. So like this you could also do. We were using a Landsat image and comparing it. You see that's an optical scene. You see what we expect to see, right? We see white. White is what we see normally. And then we see also what is interesting. We see here some structure. We don't know, but it seems as something that is covered with snow here too. We see also here some structure, here some, but it's very, very white colored, let me say like this, very difficult to see. You can look for topographic maps if you like. So then you see that this area that I've chosen here has a quite steep topographic variation. It's going from, let me say, from very high 2,500 meter to 250 meters. So it's a very steep terrain here. It seems like this, which this is a more flattish area, and this seems more steeper. So that's quite interesting for this area. Then I was using a C-band RadarSat image. It's it's a lower wavelength, so it's not so deep. However, what you start to see is some differences to an optical image here. And you see here now something like, it looks like a glacier, I would say, right? Because it's kind of look like a flow line with flow lines. And the same is actually here is kind of elongated lines. And this for me is always a sign that it's a glacier and something is moving. Whereas here where you see more, let me say, structure like topography. So for me, this would be more like could be, and this is the same that you see here, is more kind of a mountain area, right? And you see also here mountains. It's steep, right? We know it's steep. Could be that's kind of a mountainous region. At least you see already more structure, right? This is what you see in C-band with wavelengths of 5 centimeter. And this is now P-band, what you see here. And P-band looks and is penetrating much deeper, right, into snow and ice. And what is now interesting, you see much better these flow lines. It's really look like a glacier. That's very interesting, right? And the same also here. It also looks like a glacier. And these seems like a really kind of a stable area where you have topographic variations. Okay, and then I was playing, so that's the HH backscatter, and then I was playing with the Pauli scattering vector, right? This is what you could also do. And here I see now with the Pauli scattering vector different scattering mechanisms, which is interesting, much better as I would only use one polarization channel. You see here now reddish with, which is dihedral scattering. Remember, greenish volume scattering, and the bluish more, it's in principle the surface scattering. You see it, and everywhere where it's white, it means I have all three scattering mechanisms equal, intensive at the same time. So therefore, we have then the combination of these. So it means we have a lot of scattering, which is red, green, blue together here in this white area. And then you see also here very nicely this mountain, probably a little bit better. So this range here, this mountain range, quite seen very well here. And you see then this bluish area, which is surface scattering. And then again, we see here a different glacier, right? So that's one glacier, and a second glacier with different flow lines, but very, very similar to what we see on the first glacier. Okay, let us go further on, right? Because you have learned you can do this, the Pauli, but you have learned also to do images now in entropy and alpha. You can display entropy alpha. You can do it like me, and then just have a look now, oh, what do I see in entropy? How much scattering mechanism do I have over these different regions that I can separate now? Because I see I can separate this area from this region, right? This looks a little bit differently. This flowing glacier and this glacier is for me one region, and this is a completely different area, stable area. And I see an entropy that also, I have a higher entropy over this area where it's floating, where, not floating, where I have a stream, let me say a glacier, and this area where is more topographic variation. Here over the mountain ridge, it's high entropy because it's a lot of scattering ongoing. But here on the lower area, I have only one scatterer, which is interesting. And the same is for this part. And then I think the second one is an anisotropy. You don't see it because it's this part on top. You see the anisotropy, which is in principle, it's a little bit lower, this value, so anisotropy, because it's only made by the second and third eigenvalue, and the first one is gone. The first one is, you remember it's sorted, the first one is the most highest one, but then what you do with the second and third eigenvalue, you look for secondary scattering mechanisms. And also here, you see you have different structures ongoing. And then the last part, here this one should be alpha angle, and now you can see over this moving part or the glaciers, the alpha angle is increasing, so you have more alpha angle, so higher alpha angle over several parts here. Where it's dihedral, it's even high, you see it, and then this is more volume kind of part, it's reddish also a little bit, so these are the high scattered part where you have all the three scattering mechanisms together. So like this, you can build up the difference to this region, which is more a stable one. Okay, and what you can then also do, there exists a kind of a website where you can have a look for flow lines, and this was quite interesting. So it's an open source website where Antarctica is measured by very low resolution, but kind of where we have floating ice, no, not floating ice, where we have flow lines, so glaciers moving, and we have non-moving, so there's in principle velocity measured. And you see also what is very interesting with this reference, very rough reference measurements, we see the outline quite well of this region here. This is it's something that's moving, that's stable, and that's also moving. And you see this really with P-band, you can really, without using interferometry, right? That's a point here, because normally we see, let me say, velocity when you use interferometry, but here you can already distinguish the region of flow of areas where you have velocities ongoing, and you can compare them, which is normally not possible if you use let me say shorter wavelengths. So that's a very nice thing that you can already with polarimetry see the areas where you have dynamics ongoing, as for example here. So this would be my story that I could tell you if I would do tomorrow my presentation for you. So this is just an example for you what you could do in your project. And you can even go further on, right? This is a little bit what I've done then with the copolometric coherence. So you can build up, you can take only one copol phase difference. The first one is a coherence here, and the second one is a phase, and you can have a check, what do I see there? Is a phase, or again here is very varying over this very dynamic region, not all of them, but over these, let me say, flat area, which is quite stable, we see that the phase is 0, right? So that's quite, it's not changing. So like this, you could also detect this floating region, and mainly the one that is strongly dynamically, which is interesting because it means that HH and VV are differently propagating into the snow and ice over these dynamic ranges. Okay, and then you can build differences also between the cross poles. So if you use cross pole against cross pole, do you remember? I was not doing this in my example, but you could also do this. I was doing HH with HV, or I was doing VV, VH, but you could also do two cross poles. And this for us normally is a very good indicator if you would have kind of noise, right? Because actually we know it should be the same. So HV and VH should be the same over the area, so have the same contribution, so it should be 0. But like this, you see these low scattered areas, right? They are mostly affected also by noise. This is a good indicator. I can tell you then which area is reliable, more reliable in terms of having noise effect, or SNR, let me say. And this area where we have the dynamic range of the glacier is very good, so I have high coherence, which means we have perfect estimates here, and so on. So you like this, you can play around here. I was taking, for example, the difference between the Pauli 1 and the Pauli 2, right? You can also do this. You don't need to stick only with a single polarization. You can also say, okay, I do a coherence between Pauli 1 and with the Pauli 2 parameter, for example, and have a look on the coherence and the phase. So that's something also that you can just explore and try to interpret what you see. Okay, I'm not finished, you see. So you can, and then you can start to do in principle this interpretation. These are now the coherences I was showing to you before, right, where we have core and cross. So this is the ones you can just check if you see something. And I told you already, if you do it over areas, urban areas, then you see it mainly over point-like scatters quite well. But you see here now in this area, we have sometimes higher coherences. You see it here, right, over this region. And then this means if you have higher coherences, then you have also reliable phases. Everything that is dark, the phase is also not really reliable to be interpreted, right? And like this, you have a nice idea. So the green errors is everything as a combination with HH and HV, and this is a combination with VV and VH. You can see into this, you can look into the slides and have a look on this. Yeah. So there are slight differences, but not high differences. Okay, yeah, and if you like to know, I mean, we have today still one application area in terms of change detection, which will be presented after the break from Armando. But if you like to know polarimetry and more application, this was yesterday people told me when we were sitting in the evening together, it would be nice to have more applications. We just are a little bit limited in terms also of time, and the techniques are also important to be shown. So I can just recommend you go to this book. It's an online or open access book, so you can download it from the website, and then you just have a look on terms of different applications using polarimetry. What is interesting is for different areas, as said, forest, agriculture, cryosphere, urban area, and ocean. So there are different people contributing to it, and what is also interesting, there's also code inside. So you have also, if you need to have code, you can check this. There's behind, in the annex, you have also the code that you can download, and you can modify however you like. Okay, and here's just in your slides, I was just putting it there because I'm not, I don't remember if Alberto on Tuesday was presenting this, how to estimate the coherence or how to calculate coherence in Python. So that's just that you know how to do this. It's quite easy. In principle, you define a function where you have image 1 and image 2, which could be HH and VV, and you define the estimation window, right? If you like to have a small estimation window or high estimation window, so in range and in azimuth. And then in principle, your function is quite easy. You do a uniform filter with the real part and the conjugate of the one channel, HH, for example, and you smooth it in terms of looks, and then you in principle divide this by the second part, right? This is a coherence with the second image. So the first and the second of the conjugate, and the first and the second. And like this, you could in principle define your function and run it. It's just quite easy to do it and to implement it. Okay, yeah, so then I'm stopping here, and I'm open for any questions you may have. Okay. Time.
Hi. Related to the tandem-mix presentation, you mentioned that the CPD is computed with VV and HH, which is only available when the mission occurs in quad pole, right?
No, it's not. So the dual pole is always available. So you can always order dual pole data. It's a little bit different. So how we are operating is different from a mission concept as the ESA satellites. So the ESA satellites are mainly, they're having a mission concept in the beginning of the mission, and then they're always mapping it. This is I call it like a mapping machine, which is different for tandem-X. So you are able, in principle, to correct. I mean, we have a background mission, which is acquiring always data, but we can also do acquisitions specifically for certain test sites on long time series. And we mainly, you need then to say what you like to have. Do you like to have single pole or dual pole? And then we do these acquisitions.
Okay, now, because my question was when you explained the acquisition, how the signal is being acquired, I understood that firstly the satellite sends either V or H and then receives both. So I was actually understanding that to get VV and HH, it has to send both signals, and therefore it's
yes.
quad pole.
Yeah, for quad pole you need to do. It's a little bit different. So what you do here, we have on 2 satellites, we have terms of, they are separated electronically in H and V. So 2 satellites in H and V. And so like these, you could do transmit H, right? And then receive H and V if you like, or you transmit V and then you receive H and V. So what we do in a dual pole, it's a special mode where you transmit H and V, but you receive it on the same channel, right? It's a little bit easy. It's complicated, but it's easier in terms of having only HH and VV without having full pole. So it's not, we are not acquiring really full pole, this cross combination, but we are doing with one antenna, in principle, we're splitting them into half. We are receiving and transmitting in these 2. So we can do, HH and VV. Because the antenna is split in 2 halves. That's a particular case which is not so much available in other spaceborne missions. But if you like to do a full pole, then we are even, we're needing in principle more acquisition, or it's a different mode then actually.
If you could go a few slides back where you were making a comparison of this Antarctica landscape between was a few more, was the Pauli? Yes, this one. Just maybe I don't understand very well. I thought the alpha angle human shows which types of scattering do we have. So when we compare it with the Pauli and the areas where we have all of the scattering, it looks green. How do you interpret this?
You mean in principle here this one, right? This area, which is here, right? Yeah. Yeah, I mean, it's a little bit depending, right? Because what you see here, it's a little bit reddish inside. Some dots, if you would zoom in, probably you would see it. So it's a kind of transition zone here a little bit, right? Between yellow, greenish, a little bit reddish, right? You have some, it's a kind of a mix. And then you have also a little bit bluish here into it. It's very difficult to, let me say it completely, but it means it's a kind of mix that you have. And you see it actually also in the entropy. The entropy is not very high, right? So it means at least you have kind of 2, I would say it's a medium, it's a kind of 2 scatters, which is very, very strong. These Pauli, the problem with Pauli is, it has, I mean, I can't really explain what I would, I mean, you have a strong scattering from all of them. Yes, it is true in this Pauli, but the Pauli has some drawbacks because when you model Pauli, right, then you have a dependent parameters actually in order to get Pauli representation. Whereas when you use, let me say, the eigenvalue and eigenvectors really, then this is really coming from the data itself, right? It's more this physical explanation. Whereas Pauli is always good as a showcase, but you can't really separate really the scattering mechanism here very well. So that's a little bit the difference for me always between entropy alpha and the Pauli. The Pauli you do to have a first look on it, but then if you really like to know the details, you actually go to alpha and entropy. This would be my explanation. Because Pauli can be, these, the dihedral is actually sometimes modeled as a combination of HH and VV, so that's a little bit complex, but also let me say the cross pol is also kind of an oriented HH in VV. So I would not trust them so well, right? It's not a kind of completely independent measure, but it's nice as a representation, as an image. But if you really like to trust the values, then I would go really to entropy and alpha. I'm not sure if this satisfies your answer, but yeah. Mm-hmm.
Yeah, hey, thank you for the very interesting lecture. To this I directly have a question. Do you know how deep you penetrate at these sites, or how would you find this out?
Yeah, it's a good question, right? You would need a corner reflector to know where your surface is, and then in principle you can estimate the phase. So with interferometry, really the phase, the phase variation, right? In terms of when you know the surface, then you know how much you have a penetration due to the interferometric phase difference. So this you could do, but otherwise it's difficult. And even these is not really precise because you don't know really, you don't know if it's attenuated, right, or if it's completely absorbed, the signal. So it's not so easy really to get to depths. What you can do, and this is what has been shown, is actually using tomography, right? There you could try, it's like the GPR, so the ground penetrating radar, there you would see it. It's clearly as a reference station, or with tomography where you can do this digital beamforming, then you see also a little bit the structure and also the depths that you have, right? So I would go in this direction. Only using polarimetry, no, you can't do this.
Yeah.
It's impossible.
Okay, thank you. And I have a second question to the first part. Could you measure the surface height independently and then kind of back study like snow density and these processes? Because I think this could actually also be quite interesting.
Yeah, that's true. You can do this too. So what you could do is what I was showing before. So you could do the digital elevation model of the surface, but using very high frequency data, because you also penetrate there, right? There's always a problem. And then, but this is something that we have done actually. So we've done it over the Aletsch Glacier. We have used the digital elevation model of Tandem X. And then every 11 days, we have done a new one. And then you subtract one, you do a difference between the different elevation models. And like this, you get mass balance actually. So you can estimate your mass balance in terms of separating them, right? So just the height, what you get is a height difference. And with a height difference, you know how much melting is ongoing. Yes, we have done this already.
And then I guess, and then next step, combining it with the phase could be the really interesting.
Yeah, it's a good idea. You could also try to integrate this as a measure then into, probably. But the idea with polarimetry is a little bit different because with a DEM, you assume you do only one polarization. You assume you have only one kind of penetration, whereas with a polarimetry, you assume that the different polarization channels are differently penetrating into your snow, and therefore you get this information content. If they are not penetrating differently, they are equal, so therefore zero difference, zero phase. So your assumption is also when you do a DEM, right, you only use one polarization channel, but you have already one kind of penetration into it. Okay. So actually it would be easier or better than to use a LiDAR DEM as an integration, so to combine with something that you know, okay, it's really on the surface.